You will learn theory over the course of comparative
Okay, so yeah, my name is Fran. I'm a PhD student here at Oxford, and I work in a department called quantum materials. So we work with very special materials, not just your normal wood or your normal metal. And they can only be described using quantum mechanics. And so I want to start off with a question. Has anyone ever been on a train and wished it was going a little bit faster? Yeah, no, I feel you. So I grew up in London, so I spent a lot of time waiting for the tube to just kind of slowly drive along. And does anyone know why trains can't go any faster? Does anyone know what limits the speed of a train? Any ideas? Yeah? So that's a good speed limit, that trains might. Some can go a little bit faster, but do you know why it's 60? Why can't trains go any faster? Yeah? They could, yeah, it would be really dangerous if they hit something. Any other ideas? Yeah?
If it has to stop because there might be a fire in front of them in the tunnel or something.
Yeah, that's so, but imagine kind of you're in kind of the perfect kind of safe situation where you just have a track and there won't be any fire, so you won't have to hit something. What would limit the speed of a train then? What would kind of give it maximum possible speed? Yeah?
If it went really fast, wouldn't it come off the rails?
Yeah, it might come off the rails, that's right. But the reason trains can't go extremely, extremely fast is because of friction between the train and the tracks. And also because the engine has kind of only a small amount of thrust, or a limited thrust, that it can use to power the train forward. So there is a way we could actually make trains go a little bit faster. Does anyone have any idea how you might be able to get rid of one of these things to be able to make the train go faster? Any ideas? Yeah, vacuum's one idea. Another idea, imagine, right, if there was no friction between the train and the track, and the train would just go up and levitate above the track. That would be really cool, right?
No.
I think it would be cool. This is my whole PhD.
They couldn't get onto the train because it would be too high.
You could get a ladder or something to get onto the train. Trust me, it works, it works. So imagine now we're all very enthused about a levitating train. And does anyone have any idea how we might be able to get a train to levitate in the first place? Yeah?
The reaction of magnets, if they don't want to come together, then they could.
Yeah, that's exactly right. So if we're going to use magnets to try and levitate things, so I've got two bar magnets here. And so if you have a North Pole, South Pole come together, right, they attract, they really like that sort of thing. But if I put two North Poles together or two South Poles together, they're not going to like it. They're going to repel. So imagine you kind of use this repelling force, right, to make them levitate. So I've got kind of North Pole, South Pole here, and then North Pole, South Pole here. Who thinks that they're going to levitate when I drop one onto the other?
Yeah.
Okay, well, moment of truth. 3, 2, 1. Oh well, that's that. And the reason why it doesn't work is because these levitating, so these are just regular bar magnets, and they're actually metastable, so they're not very stable. If you have them perfectly one on top of the other, it'll be stable, but as soon as it slips a tiny amount, then they're just going to kind of snap together and fall over, just like you saw there. So that's quite a big problem, because obviously you want your train to be moving. So as soon as the train moves a little bit, then it's going to stop being stable, and then it's just going to flip around and fall over. Does anyone know how we might be able to overcome this problem? Yeah?
If you only use one magnet against one magnet.
I think we've still got the same problem here, because this is one magnet and this is one, and then we still have...
Only one end without another end.
So that's a very interesting idea, to use just the North Pole on its own, just the South Pole. And we think in physics they should exist, but actually physicists haven't even been able to find them yet. So we're going to have to try and work with things at the moment that we've already discovered. Does anyone have any other idea? Well, how about using a different kind of magnet? Has anyone ever heard of a superconductor before? Yes, someone has heard of a superconductor. Now, superconductors are really interesting because they are a quantum magnet. So you cannot describe these magnets with normal classical mechanics that kind of describe balls rolling down hills and kind of normal trains moving along, you have to use quantum mechanics. And they've got some very interesting properties. So superconductors have no electrical resistance. So who's ever touched a wire when it's part of a circuit and it's got a little bit warm? Has anyone felt that? Yeah, so actually that's because the wire has resistance, and superconductors, they have no resistance. So if you put a current through a superconducting wire, the current will keep going round and round, and it won't lose any energy to heat, and it'll just keep going. And so there've been experiments where this current has been going for tens of years. So that's pretty neat. But the thing that's really important for us today is that it acts like a magnetic mirror. So if you get your superconductor, so I have got a superconductor here, and you put it near some magnets. I've got some magnets here. If you put one on top of the other, the electrons and the atoms, they're going to rearrange themselves inside the superconductor in such a way that it will become a magnet, but it will be a magnet that perfectly repels these magnets, which is pretty neat. So I've got some magnets. I've got some nice magnets here. I've got a superconductor. Who thinks this is going to levitate when I put one on top of the other? Okay, well, you've got big expectations. So 3, 2, 1. Oh, well, this is just a talk full of disappointment. So does anyone know why that didn't work? Any ideas why it didn't work? Yeah?
So when it's reflected, it's kind of reflected the opposite so that they do attract?
Not quite, no. So it is it's reflected so that it perfectly repels. So actually the reason is because this is at room temperature. So this is a superconductor. It's kind of, at the moment, it's a bit like a ceramic, like something you get in a fancy bathroom or fancy plates. And it's pretty boring. So we need to cool it down. We need it to be really, 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 really cold. And we need it to be below its critical temperature. And when the temperature is below the critical temperature, then it's superconducting. And so this one has a critical temperature of like minus 150-ish degrees. Does anyone know how we're going to get down to that sort of low temperature? Yeah? Bingo. And here it is. So has everybody heard of liquid nitrogen before? Yeah, liquid nitrogen is wicked. It's you take nitrogen from the air, and that means it's actually pretty cheap. It's about the same price per litre as milk, but it's a lot less weird to throw around. And so I just take a little bit. It never gets old. It is very, very cool. And so yeah, nitrogen, you take it from the air. So that means if I put a balloon full of air in here, the air inside will also liquefy, right? So these are balloons I blew up earlier. And so, who thinks they're going to explode? They're only going to explode if they're low-quality balloons. I think they worked fine earlier. They're just stuck together, that's fine. Because I blew them up with a certain amount of air. I put them in here, and then the air condensed down and became a liquid, and the balloon shrank. But now, the air is going to evaporate, hopefully, and then, hopefully, it'll go back to being the same size. I think it's okay. So yeah, so that's very cool. And the main point of that is that liquid nitrogen, when you turn it from a gas to a liquid, it actually condenses down quite a lot. So I've got a little bottle. Look, it's got the tiniest amount of nitrogen in there, and I'm going to stick a balloon over it, and I'm going to try and work out how much gas that's going to produce. So give it a little shake. So you see there, that tiny amount of nitrogen is blowing up the entire balloon. And in fact, the nitrogen, when it goes from being a liquid to being a gas, it increases by 700 times in volume. So it's actually got a little bit dangerous, and you've got to be a little bit careful. Okay, I'm just going to intervene. Okay, I'm glad that's the highlight of the talk. So it increases by 700 times in volume when it goes from being a liquid to being a gas. So it is a little bit dangerous. You might have heard a story a few years ago now. So it became very fashionable for a while to put liquid nitrogen inside drinks because, I mean, it's really neat. Look at it. It's really cool. And you can put it in drinks, and it freezes things really quickly, and it is really interesting. But obviously, if you have a drink which has got something which is like minus 200 degrees in it, you generally wait for the minus 200 degrees bit to evaporate out, right? I mean, it's not just me. But someone in the news a few years ago drank a cocktail which still had the liquid nitrogen in it, and then the liquid nitrogen went down her throat, expanded 700 times in her stomach, blew up her stomach. She had to have an operation to have her stomach removed. She's still alive, so it's okay. But the point is, don't drink this, is what I'm trying to say here. And so I've got some nitrogen, and I've got my superconductor here, and I'm going to try cooling it down, see what happens. And so now, the little superconductor, the little puck in there, is cooling down. And what happens when it goes through the critical temperature, it goes through something called a phase transition. A phase transition is basically when you get something and it changes its properties after a certain temperature. And there are lots of different examples. When you have water boiling at 100 degrees, that's an example of a phase transition. When you have water freezing at 0 degrees, that's an example of a phase transition. And so I'm going to show you another phase transition. So I've got this rubber rod, and can you tell me, how does it feel? Does it feel brittle or soft? Yeah, so it's like soft and bendy, and if I hit this with a hammer, I mean, not particularly exciting, but whatever. And so I'm going to put in the nitrogen. What happens when I put in the nitrogen is that it heats up the nitrogen that's immediately around it, because the rod is about 200 degrees hotter than the liquid nitrogen. And so when it heats that up, it turns into a gas, and then that pushes more liquid nitrogen through the rod. And now it's stopped, which means it's at minus 200 degrees. And the rod has gone through a phase transition where it's changed its material properties. And now it shatters like glass, which is pretty cool. And so it's not just that, it's not just your rod. You can also do with flowers. So flowers, they're made from plant cells, which are mainly water. And so obviously water is going to be frozen at minus 200 degrees. So just give it a little moment. There we are. And it shatters like glass. So this is really good if you're having a really bad Valentine's Day. A friend told me that. So that's pretty neat. I mean, you can smash a lot of things, but let's try and be a little bit constructive now with our phase transitions and see how it goes for our superconductor. So I'm hoping our superconductor is pretty cold now. And I'm going to put it on here. We see that is levitating. That's pretty neat. And so it's going to be heating up now because it's obviously in the air, which is much hotter than the superconductor. And once it goes above the critical temperature, goes through the phase transition, and then stops superconducting, becomes boring again. So that's pretty neat, I think, anyway. So this is when it acts like a magnetic mirror. So you get your superconductor, you cool it down, it starts superconducting, and then what happens is it arranges the electrons inside itself so that it pushes all the magnetic field out and it perfectly repels it. So that's quite good, but it's not particularly stable. It can fall off quite easily, so we need something a little bit better in order to make our superconducting train. But fortunately, we've got science on our side here. So if I actually cool down the superconductor inside the magnetic field, it's going to do something a little bit different. So add a bit more nitrogen. That looks pretty cold. And now we're superconducting again, but this time it's trapped the magnetic field inside itself. So now you can have superconducting roller coaster, which is like basically the reason I was doing a PhD. So I can do superconducting roller coaster. And now it heats up, goes through the phase transition, and stops superconducting. So that's a different kind of superconductivity. And that's called quantum locking. So what happens there, you get your superconductors, so like super boring, and then you put it in the magnetic field, and then it pretty much holds on to the magnetic field inside the superconductor, and then it's stuck inside. So it's basically the same as kind of, I don't know, if I would hold this bucket like this for the first one, the magnetic mirror, but then if I put my arm through the bucket for the quantum locking, it's a little bit more stable. So that's the sort of thing we want to be using with our train. And a little bit of history. Superconductors were discovered by this guy, Cameling in Leiden in the Netherlands in 1911. And he discovered mercury superconducts at minus 269 degrees. So that's a little bit colder than liquid nitrogen. Does anyone know how we're going to be able to get to a temperature colder than liquid nitrogen? Yeah? Dry ice is actually not going to work in this case, I'm afraid. I think dry ice is a little bit warmer than liquid nitrogen. Any other ideas? Yeah? That's a very good idea. So these days, we actually use liquid helium because that's really safe and it doesn't react with things. But back in Cameling day, they did use liquid hydrogen. But as you probably know, if you have hydrogen and then you have a flame, it will set on fire and blow up enormously as soon as it reacts with the oxygen in the air. And so it's not particularly safe. So there were a few of the early PhD students in superconductivity did die because they were smoking their pipe. This is all back in the day where people like still wearing suits and smoking pipes in the lab. And they were smoking their pipe and then the flame from their pipe caught onto some of the hydrogen and blew up the lab. But generally this doesn't happen anymore. I mean, I don't like taking risks. I don't even go ice skating. So I think I wouldn't do this if this was very dangerous. And so superconductors, they're really exciting, but they're actually useful. It's always very important when you're doing science to think about why these things will be useful for society, not only to justify it to yourself, but also to get funding. So does anyone recognize that thing up in the corner? Has anyone seen that before? Yeah? Do you know what it is? Anyone know what it could be? Yeah, so has anyone heard of the Large Hadron Collider before? So that was big in the news with the Higgs boson. Well, so in the Large Hadron Collider, they got loads of particles, and they go really, really, really fast in circles. And the way you get the particles to go around in circles is by using magnets. And we've got to use these superconducting magnets, because there you can make really, really big magnets that are able to push the really fast particles around in circles. And then you can also use them in telescopes. So you can use superconductors and very special detectors that allow you to see very dim and far away stars. You can use them in trains. So train one is really neat. Has anyone ever been to Birmingham Airport before? There is a maglev train between Birmingham International Station and Birmingham Airport, which is pretty neat. So I went on that for the first time recently. I was definitely more excited than any of the kids on there. And so the Birmingham Airport one doesn't go very fast, but maglev trains can go incredibly fast. They can go up to 600 kilometers an hour, which I think might be the land speed record, so pretty quick. You can also use them in quantum computers. So quantum computers are a very special kind of computer that allow you to calculate things really, really, really quickly, so no more waiting for the computer to load. You can use them, obviously, because there's no resistance. You can use them in wires to transmit enormous amounts of current over long distances without losing any energy. So that would be amazing. Imagine if you could get transmission lines that don't lose any energy. And finally, MRI scanners need a very big magnet. And if you want to have a very big magnet, what are you going to use? It's a superconductor. So superconductors, they're basically everywhere. And one question I get a lot actually with the train is how does it hold the train up? And that's really interesting because superconductors can actually hold up to 70,000 times their own weight just with the force of repulsion. So I think that's pretty neat. So I'm going to finish off with one final example of how you can use superconductors, and that's to make a levitating sumo wrestler. So as you see there, it can even hold up the sumo wrestler. So thank you very much for listening. I've got a little train down here at the front. If any of the kids or parents would like to have a go pushing it around, seeing how stable it is. Anyone want to have a go? Yeah, just come down to the front. It's fine. And does anyone have any questions? I'm just going to cool this down. So just give it another moment. Can you see all the droplets of the liquid nitrogen there? So you see the levitating train. Does anyone want to give it a little push? See, they can just go for it. Just be gentle. Yeah, cool. Well, thank you very much for coming. I think if you don't want to stay for the other talks, please go out of this door. Apart from that, I hope you have a nice rest of your day.